Welcome to MarkScheme, Exponents and Logs. Everything you need made visual. Here's a question that sounds impossible. What power of 10 gives 500? 10 squared is 100? Too small. 10 cubed is 1,000? Too big. So the answer is some number between 2 and 3. But which number exactly? There's a tool built precisely to answer that. It's called a logarithm. And by the end of this video, it'll feel obvious. The exact power is 2.699. Here's exactly what we'll take off, straight from your syllabus. Two subtopics at once, 1.5 and 1.7. Because exponents and logs are two sides of the same coin. The index laws for whole number and fractional powers. Logarithms, base 10 and base e, defined as the inverse of an exponential. The three log laws. And change of base, plus solving exponential equations. One thing you can relax about. Higher level pushes logarithm work further. But none of that is on your standard level paper. Start from what a power really means. 2 cubed is just 2 times. 2 times 2. 3 factors of 2. 2 squared is 2 more factors. So multiply them, and you're counting factors of 2. 3 of them, and 2 of them. Watch what happens when we merge them into one line. 3 factors plus 2 factors makes 5 factors of 2. 2 to the 5th. Nothing was memorized. To multiply powers of the same base, you simply add the exponents. There's your first law. The same counting logic gives the rest. Dividing? You cancel factors top and bottom, so you subtract the exponents. A power of a power, m factors, taken n times, means you multiply the exponents. And 2 neat consequences fall out for free. Any base to the 0 is 1, because a to the m over a to the m is a to the mn minus m, which is a to the 0, and equals 1. And the negative power is just a reciprocal. A to the minus n is 1 over a to the n. A minus sign in the exponent never makes the number negative. It flips it. Now the clever part, fractional powers. The index laws force their meaning. We don't get to choose. Ask what x to the 1/2 must be. Multiply it by itself. By the add the powers rule, that's x to the 1/2 plus 1/2, which is x to the 1 just x. So x to the 1/2 is the number that squares to give x. That's the square root of x. The root and the fractional power are the same thing. The same argument with an n gives the general rule. X to the 1 over n is the nth root of x. And for a full fraction, m over n, split it up. The bottom number is the root. The top number is the power. So x to the m over n is the nth root of x, all raised to the m. Or equivalently, the nth root of x to the m. Bottom is the root. Top is the power. That single sentence handles every fractional exponent you'll meet. So back to our hook. We want the power of 10 that gives 500. Undoing a power is exactly what a logarithm does. Log base b of y is defined as the power you must raise b to in order to get. Read it out loud. Log base 10 of 500 is the power of 10 that gives 500, which is 2.699. Two special bases get their own buttons. Base 10, written just log, and base e, written ln, the natural log. And here's the picture that makes it click. Plot y equals 10 to the x in blue. It rockets upward. The logarithm is its inverse, so its graph is the exact mirror image. reflected across the dashed line, y equals x. Watch the exponential fold over that line and become the log curve in purple. Inverse means each curve simply swaps input and output. The blue curve sends 0.5 up to about 3.16. The purple log takes that 3.16 straight back down to 0.5. The point bounces between them. X goes in, the power comes out, and the log runs it in reverse. Before the loss, 3 facts worth knowing on sight. Log base a of 1 is always 0, because a to the 0 is 1. Log base a of a itself is 1, because a to the 1 is a. And the single most important restriction: the thing inside a log, the argument, must be positive. You can never take the log of 0 or of a negative number, and that will matter enormously in a moment. And here's why logs were invented at all. A logarithm turns multiplication into addition. The log of a product is the sum of the logs. Centuries ago, that was revolutionary. It let people replace hard multiplications with easy additions, which is exactly how the slide rule worked. That single idea, swapping times for plus, is the beating heart of the log laws we'll prove next. Where do the log laws come from? They're the index laws wearing a disguise. Write x as b to the p and y as b to the q. Remember, a log is just an exponent. Multiply x and y, and they add. The powers rule gives b to the p plus q. Now take the log base, b. It reads off that exponent p plus q, which is log x plus log y. The log of a product is the sum of the logs, because multiplying numbers means adding their exponents. Run the same argument with division, and you subtract. The log of a quotient is the difference of the logs, and the power comes straight from the power of a power rule. The log of x to the m is m times the log of x. The exponent slides out to the front, 3 laws. All just the index laws seen through the logarithm. One warning coming up. These only combine logs of the same base. One law left, and it's the one that makes your calculator all-powerful. Change of base. Say we want log base b of a. Call it x, so b to the x equals a. Take a log of both sides. Any base? Say base 10. The power law drops the x to the front. X times log b equals log aa. Divide. And log base b of a equals log a over log b. Why care? Your GDC only has 2 log buttons, base 10 and base e. But with change of base, you can evaluate a log to any base. Log base 2 of 10, just type log 10 divided by log 2. 3.32. No special button needed. Now the payoff of the whole video. Solving an equation where the unknown is stuck in the exponent. A to the x equals b. You can't just undo it by dividing. X is up in the power. So take the log of both sides. The power law slides the x down to the front. X times log a equals log e. Now x is on the ground floor. Divide, and x equals log b over log a. Take logs of both sides, then divide. That single move solves every one of these. Read the idea plainly. The x is trapped inside the power, and the logarithm is the one tool that frees it. Take logs of both sides, then divide. Commit that to memory. Let's put it all to work. My numbers, exact IB style. Part A, simplify. Square the bracket first. 2x cubed, all squared, is 4x to the 6, times x to the minus 4 over x. Now just add and subtract exponents. 6 minus 4 minus 1 is 1. The answer is 4x. Part B. A fractional power. 27 to the 2/3. Bottom is the root. Top is the power. The cube root of 27 is 3. Then squared is 9. Part C. An exponential equation. 3 to the x equals 20. Take logs of both sides, then divide. X is log 20 over log 3, about 2.727, which sits nicely between 2 and 3, just as we'd expect. Part D uses the natural log. E to the 2, x equals 7. Since ln undoes e directly, 2x equals ln 7. So x is ln 7 over 2, about 0.973. Now a harder one that pulls the whole video together, and it hides a trap. Solve log x plus log x minus 3 equals 1 base 10. First, use the product law backwards. Log x plus log x minus 3 is the log of x times x minus 3. So the log of that product equals 1. Now undo the log. Log base 10 of something equals 1 means that something is 10 to the 1, just 10. So x times x minus 3 equals 10. Expand and tidy. X squared minus 3, x minus 10 equals 0. That's a quadratic. Factor it into x minus 5 times x plus 2, giving x equals 5 or x equals minus 2. But here's the whole point of the question. Check both solutions back in the original logs. If x were minus 2, we'd be taking the log of a negative number, and that is undefined. So we reject x equals minus 2. Only x equals 5 survives. Always test your answers back in the log. The argument must stay positive, and examiners set this trap on purpose. Now with the exam graph, other channels skip. 1. For any equation with the unknown in the power, take logs of both sides and divide. X equals log b over log a every single time. 2. On your calculator, use the log and ln keys directly, and for an unusual base reach for change of base. Log base 2 of 10 is just log 10 over log 2. 3. Remember log on the calculator means base 10, while LSN means base e. Don't confuse them. 4, the big one. On paper 1, leave your answer exact. Log 20 over log 3, not a decimal. Paper 2 wants 3 significant figures. 5. The log laws only ever combine logs of the same base. Different bases must be converted first. And 6. The one from our last example. Whenever you solve a log equation, substitute each answer back and throw out any that make the argument 0 or negative. Before the recap, the 4 traps that quietly lose marks. 1. The biggest. Log of x plus y is not log x plus log y. Only products split. Log of x times y does. A sum inside a log stays put. 2. The thing inside a log must be positive. Log of 0 or of a negative number is undefined. If your working produces 1, you've taken a wrong turn. 3. Don't confuse the power of a power rule, where you multiply the exponents with multiplying powers, where you add them. And 4. A negative exponent is a reciprocal, not a negative number. To the minus n is 1 over a to the n, and stays positive. Dodge these 4, and this topic is free marks. And that's SL 1.5 and 1.7. Both fully covered. The index laws for integer and rational powers. Logs as the inverse of an exponential. The log laws with change of base. And solving exponential equations. Higher level takes logarithms further, but nothing beyond this is on your standard level paper. Next in the course, proof and identity. How to actually justify a result. For more, that's markscheme.app. See you there.